All right, how many people have done exercise C already, just so I know? All right, so okay, so I'll get people started and maybe show. Okay, let me try to get it on all the other screens as well. All right. So this is Python Tutor, so it's kind of, well, it's helpful for some people. Actually, where's my, yeah, so it's helpful for some people. So here's what that looks like. So here, it's kind of visualized with arrows instead of addresses, right? So what's shown here is that you have L, that's a global variable. So that's what the global frame means. And then here it says, well, L consists of two elements. So one of them is just 7. And then the other one is the list 5, 6. Okay, so the way it's visualized is L is a list. So its 0th element is a list, and its first element is 7. So here, as a shorthand, what they do is instead of saying, oh, like the first element is also an address, they just say because it's immutable, meaning that because it's an integer whose content's going to change, they just write 7 here. Really, it's an address of where 7 is stored. And then the first element, so element number 0, is this list. So this list is a separate thing. So that's stored separately, and that's the 5, 6. So now we say, okay, so L is this new list whose first element is L at 0. So that's what's shown here. So it's a list, and its first element is now itself a list. And this is the same list. This is the list 5, 6. So this is where kind of knowing the actual memory model does help. I'm not sure if you can, if my mic, is my microphone work? Are you fine back there? Well, you wouldn't know. Oh, okay, you're fine. So this is where kind of having the actual memory model helps you know what's going on, because I think you can kind of say, well, we never created a copy of 5, 6. So that is why it's like this. But otherwise, like that's the only kind of reasoning you would have is like, I never created a copy of 5, 6. So it must be that there is just one copy of 5, 6 in memory. But otherwise you wouldn't know. So if you think in terms of the memory model, you would know that here we are on the right-hand side. We say L at 0, we never created a separate list. So that must mean that we copied the address of 5, 6 over here. So, okay. So now we are at L101 is equal to 7. So that's like that. So what happens when you say L1 at 0 at 1 is equal to 7? Well, L1 at 0 is this list. L1 at 0 at 1 is this guy. So that means that this guy gets changed to 7. All right. And of course, if you think back, well, does it matter for L? Well, of course it does, because L's first element is this guy, and then the second element is 5, 7. So that matters for L and L1 because they share this common list, this 5, 6, that's now 5, 7. And now you're saying L1 at 0 is this new thing. So again, just thinking in terms of, the rules for the rules that we had is, well, on the right hand side, we got to create this new object, and the content of this new object is 7. And then we're saying L1 at 0 is this new thing. So that means that L1 at 0 used to be 5, 7, and now it's going to be a new thing. So that's what we'll see, is L1 at 0 is this. And then you print it. So L is what? L is 5, 7, and then 7. And then L1 is a list whose contents are themselves a list that contains 7. So that's going to be like this. So a list with one element, and that one element is a list that contains 7. So I'm now going to ask you to go back and actually do the memory model as well. I think it's useful. So let's take 5 minutes to do that. Yeah, so just write out the kind of memory model thing. How many people are working on the exercise? Okay, yeah, going. Just making sure. You can talk to each other, by the way. Just during the lecture, you're not supposed to. Right now, it's fine. I'd have it backwards. All right, so let's do a few of the lines. So here what you have is you're creating a compound object, right? So that means that you first need to place a 5, 6, and 7 in memory if they're not already there. As we saw in Python 3, they are anyway. And then you need to put 5, 6 in memory. So if 5 and 6 and 7 are over here, then 5, 6 can now be placed in memory. So at 1020, at 1040. And now that this is in memory, you can create the big list L. So the first element of L is going to be the 5, 6. So this is going to be at 1080. And then the 7 is at 1060. So at this point, you're now ready to say in the variable table, L is at 1100. So the second one is the tricky one. So here we're saying we have a new list. So on the right-hand side, it's a new object, but we never create a copy of L at 0. So that means that what we got to do is we just got to take L at 0, so at 1080, and just copy it to the new list. So that's going to be at 1080. So at this point, once that's written out, that's pretty much it. Right, so this is at 1200. So now we're just saying, okay, like L1 at 0 at 1, what's L1 at 0 at 1? Well, L1 is 1200. L1 at 0 is the list at 1080. At 1 is this guy. So that's now 7. So this means that this becomes 1060. And then L1 at 0. So L1 at 0 is this guy. And now we're saying it's a new list that contains 7. So this new list, we have to first create in memory. So this is going to be at 1060. And now L1 at 0 is 1220. And now it's the same thing that we saw before, where because basically we never created a copy of this guy 5, 6, that means that when we modify this list 5, 6, that affects every list that has the original 5, 6 in memory. So this is how I think about this when I actually kind of write code and say, like, is it going to be modified? Is it not going to be modified? I ask myself, have I ever created a copy of 5, 6? If not, well, that must mean that when I'm modifying the 5, 6, that's going to affect all sorts of things. On the other hand, I'm saying, okay, like that's a separate list. Okay, that means that I change element 0 and L1. Well, L1 is not an alias of L. So that is how I ended up thinking about it at the end. That might not be necessarily how you think about it. So some people write out the memory tables, some people do the diagrams. I think those are all okay ways. I would say that if you work through exercise C and you really understand what's going on there, I think you're basically good in terms of the kind of the memory table. Everything else is a little bit risky in that sometimes so by the way, like the exercise C is like one of my most popular things on YouTube. So you can just look up exercise C ESC180 in YouTube. It's there. My channel is not yet monetized, so like no financial interest in that. But I'm told I will be able to apply in November. So like remove your ad blockers. Although I don't think those are allowed anymore anyway by YouTube Red. So okay. So okay, all right. That's this. So one thing that we haven't done and I want to quickly do now is slicing, because slicing is kind of like a shorthand for doing dot copy. So basically what you might do is you might say L is, let's say, whatever. So what you might do is you might do something like this if you want to create kind of some kind of subset of L. So L1 initially is going to be empty, and then you do for I in range kind of start and step for whatever start and end step. And you'll append L at I to L1, right? So what does it do? Well, it makes a new list. So this is L1, and that's going to be this new list. And then initially it's going to be L at start, and then it's going to be L at start plus step. And then it's going to be L at start plus 2 step, and so on, where you go up to but not including end, right? So might do something like this. So for example, you might do like for I in range, I know, so like 1 and then 5 and then 2. 1 dot append L at I, and that's going to be whatever, L at 1 and L at 3. So a shorthand for this is slicing. This is going to be L from start to end in steps of step. This is all it is. So you might, for example, write L from 1 to 5 in steps of 2. Right. So you can also do something like L from, let's say, 4 down to -1 in steps of -1. So that's going to be L at 4 and then L at 3. And so on down to L at 0. So here you're starting from 4, you're going down to, but not including -1, so down to 0, and you're going in steps of -1. So you can omit step because step is 1 by default. So L from 1 to 3 in steps of 1 is the same as L from 1 to 3. So can also omit start and end. So you can say L from the beginning and up to 3. And that's going to be L0 and then L1, L2. And you can do something like L this. So this is just L0 and so on up to, in this case, 1, 0, 1, 2, 3, 4. So up to L at 4. So this is also known as L.copy, right? Because this is just from start and up to the end, just do all the elements without making copies of that element. So so I say like L everything is the same as L.copy. So that's what's known as a shallow copy. Why is it a shallow copy? Well, you can see why over here, right? So here you're creating a new list, but you're not creating a copy of L at 0, you're not creating a copy of L at 1, you're not creating a copy of L at 2. Make sense? So what you can do is, for example, if you want to create a deep copy of this guy, so what can you do? Well, if you know the structure, you can say L1 is a copy of L at 0, and then L at 1. Right? So what this does is it takes L at 0, so 5, 6, and then it creates a copy of the list 5, 6. And puts it in memory, and L1 at 0 is the address of a copy of 5, 6. And here you're saying L1. Why are you saying L1 and not L1 everything? Well, 7 is not a list. You try to do 7 everything, it'll just crash, right? So you cannot say like 7 everything. That doesn't make sense. So here I relied on knowing the structure of L. So knowing that this is a list and this is not something that I need to make a deep copy of in order to make a deep copy of L1. So note that the way we could do it before, if we knew that it was a list of lists of integers, is we said like L1 is nothing, and then for E and L, L1 append. So in this case, we can say E.copy or E everything. And the reason we could do this is we knew that this was a list and this was a list. So in that case, we could say, well, make a copy of the 1, 2, and make a copy of the list that contains 7. So that was fine. This is not something that we can do over here. Are people tagging me again? No. Oh, people are messaging me. Okay. So, all right. So that's like that. So for now, we can only make a deep copy of an object whose structure we know. So if you don't know the structure of an object, it becomes difficult. We'll see how to do it later on, but you can kind of see the difficulty, right? So imagine that L is whatever, something like this. Or in fact, don't need the 0, something like this. How do you make a deep copy of it? Well, if you knew that it was however many 7 layers deep, you could do it, right? So you would say, what would you say? You would say L1 is a copy of the copy of this kind of deal, right? So how many zeros do you need? Okay, I'll just remove a few. Okay, so none. So that would be, so here L is here, need a copy of L at 0, need a copy of L at 0 at 0, need a copy of L at 0 at 0 at 0, need a copy of L at 0 at 0 0 0. So need a copy of this thing. So that's what we'll do. Right? Oops. So I'm making a copy of this guy. And then all of that should now be enclosed in the appropriate number of square brackets so that I'm creating a new list. And then inside here, there's a copy. So almost not necessary to do anything because all the information about the structure is in the square brackets. 1, 2, 3, 4, 5. 1, 2, 3, 4. And then the innermost one I can copy. Well, almost didn't need to do it. Might as well have just created a new list anyway. So here what they did is they created a copy of this guy. Everything else I needed to just contain the structure in the new square brackets anyways. So it might make more sense if you said, okay, like this is 12 or whatever, and I want to create a copy of this 12. So to be clear, the reason I'm doing this is if I'm making a list like this, let's just make a modest 3. So then, of course, like M1 equals M, now M1 and M are aliases. So that means that if I change the contents of M, I'm changing the contents of M1 as well, right? So if I say something like M1 at 0 is high, M is affected as well. Right? So what happened here is the first element of M used to be this guy, and now I just replace it with high. So, okay, so that doesn't work. So if I say something like, so M is now just high. So let's say that I say M1 is M shallow copy, like this. What happens? So I say M1 at 0 equals high, M is unaffected because M and M1 are not aliases, right? So now M1 is this, M is still hanging out there. However, if I say M1 at 0 is equal high, we run this. Can't do this now. So M1 is now this, and M is now this as well. So why is that? Well, it's because M1 at 0 is this guy. I never created a copy of M at 0. So I modify the contents of M at 0. Well, that's the same as modifying the contents of M1 at 0. Does that make sense? Question. So, okay. So what could I do now? Well, I could say, oh, okay, fine. So instead of doing this, I'll say M1. So I want M1 to have the same structure as M. So I want it to be a list within a list within a list. So I'll say, okay, I'll create a new list. And in that list, I'll have M0, but not M0, the copy of M0. Right? So I run this, and now M1, I need to restart M. So I run this, and it's like this, and I run this, and it's like this. And now M1, M and M1 are separate lists. And also M1 at 0 is a copy of M at 0. It's not the original M at 0. So those are not aliases either. But in the same way, M at 0 is an alias of M1 at 0. Right? So I need to do one more step and create a nested list with 2 lists in there and then have a copy. And that would work. But basically, I'm storing all the information now manually. Might as well have like retyped M completely, especially given that it didn't have any contents anyways. Make sense? So that's just setting up the problem. I'm not going to solve it right now. That's just kind of what it's like. All right. So, okay. So what I suggest is, so I kind of decided to be nice and well, and like as it turned out, I had to compensate you for the mess up of like U of T. So you didn't have the memory model of the midterm. I know some people might not have been happy about it, but it's definitely gonna be on the exam. So no, yeah, like it doesn't matter what U of T does. It's definitely on the exam. So what I suggest is doing kind of exercises A, B, and C again. So the video solutions are on the internet. I also told you now, so those are now also on the internet. So just practice a little bit, try Python tutor. Yeah. Okay. So for the last couple minutes, I want to talk about the bonus problem on the midterm because I thought it was kind of amusing, although I understand that the midterm is not the time that most people are looking to be amused. Nevertheless. So the idea there was to use Leibniz's formula to obtain the digits of pi to arbitrary precision. So the obvious problem is a float doesn't have an unlimited number of digits, right? So it just has like 18 or something. So you cannot just say, I'll just do a float. Well, if you could, you would just do math.pi anyway. So on the other hand, integers do have unlimited precision, right? So that means that integers can store as many digits as possible. So basically what you should have done in this problem, maybe there were other ways, but like not, there were definitely, but just like not easy ones. So the easy way is to figure out, okay, I'll just use integers in order to store my answer. Okay. So how would you store the answer in an integer? Well, if this is all you have, you could just say math.pi times whatever. So 1e18, let's say, and convert it to an integer. So here you have like the digits of pi stored as an integer, right? So the problem is, so in fact, a few more, but the problem is like at this point, those are fake digits. Those are not actually the digits of pi. You only have a limited number. So you can try kind of, let me try like a very large number. Those are like not real digits of pi. So what I want to do is I want to actually store a very large integer with the actual digits of pi in it. So how to do it? Well, so we go back and we look at the Leibniz formula. So that's the same thing that you had in the lab. So I'm not going to kind of belabor it. So what we do basically, so that's just from Piazza. I'm just like removing the annoying red squares. So the only change from what we've done in the lab is I want to store my answers as integers. And the reason is for a while it's going to work with floats, but you need too many digits. The float is just not going to be able to store the digits. So what do? We say, okay, I need this many digits and digits. So I'll set up this factor. So it's going to be a very large number. It's going to be 4 times 10 to this power. So if I multiply a float by this much, the integer part of the product of the approximation of pi and this guy is going to be so large that all the digits are going to be in the integer part that I care about. I need the first 10 digits anyway. And then what I say is, okay, so I'll just keep adding this term that you have in the Leibniz formula, but times factor. So if you try to divide a very large number by whatever using normal division, it's going to say you can't because the integer is too large. Right? So what I'm going to do is I'm going to first multiply this guy by factor. So that's going to be a huge number. And then I'm going to say divide it using integer division. And if the factor is large enough, then of course there's going to be rounding. It's not precise division anymore, but the factor is so large that it doesn't matter. It's close enough. And when do I stop doing this? Well, I stop when the last digit of the integer, so like the huge factor times my approximation of pi, changes by less than 1. Right? So at some point, kind of the last digit, I'm going to settle on it, and it's not going to change. So at that point, I'm going to stop. So because my factor is actually an overestimate, it's like plus 10, then I'm basically going to stop when the 10th digit after the one that I need to doesn't change. So that's got to be close enough. And that's because those terms get smaller and smaller, right? And you also do plus minus. So if the 10th digit doesn't change, it's fine. So okay. So that's what, so that if I run it, so here I'm also just going to print my current estimate for pi 10. If I run this, it's going to take a very long time, but eventually it's going to give me a very large number whose first digits are the digits of pi that I'm looking for. So let's say that I say Leibniz pi 6 and I run this. What's going to happen is it's going to go on and on, but you see that it already kind of figured out the first 4 digits. It's extremely, extremely slow, but eventually it's going to get there because it's the formula. And it's fine. Like on the midterm, you didn't have to run it. You just had to write it. So with this idea, you're kind of almost there. Now what you need to do is you just need to extract the digits, which I see I don't have time for. But extraction of the digits is on Piazza. I'll see you Wednesday. Bye. But nobody likes the Smarties, eh? Yeah, but you get the Bye.
Slice it. Because
Okay.
I think one part there might be thing like so. For like here, should this be just nothing in the middle?
I mean, -1 is fine, I believe.
But doesn't -1 go back to output without for -1?
In this case, it does.
So it should be
I mean, you can put nothing but -1.
Oh, it doesn't work. I think I tried it. I think it always.
I think it should.
Okay.
Oh, I'll take another one.